let's begin. Welcome to this week's South American Geometry webinar. As usual, you can find in the chat the instructions for joining, subscribing our mailing list, so you can text or email the word webinar to geodiff@unicamp.br, or you can send it via WhatsApp to this number, and you'll be added to the mailing list. You can also check our future talks and previously recorded talks on the links provided. So tonight we have a special host, the Professor Marcos Alexandrino from University of São Paulo, who is certainly more knowledgeable in the guest area of expertise. So let me pass on the chair to him.
Okay, thank you very much. So it's my pleasure to introduce our dear friend, Professor Ivan Struchiner, also from São Paulo. We'll talk today about singular Riemannian foliations and the Lie Groupoids. So Ivan, you have the floor.
Well, thank you very much. Thank you to the organizers for inviting me. And so let's get started. So I'm going to talk about singular Riemannian foliations and Lie Groupoids. And I'm going to try not to assume that people have previous knowledge on Lie Groupoids or singular Riemannian foliations. So what I want to discuss a lot is the motivation for the project. And this is I think it's a long project, and we're at the very beginning of it. So it's ongoing work. I'm going to present the first results and try to motivate why we care, why we want to study this. So our original motivation is to try to generalize known results from regular foliations. And I'll tell you what foliations are very soon, but regular here just means that all the leaves of the foliation have the same dimension. So the case of singular Riemannian foliations. And some of these results, or for example, the Molino-Struchiner theory for regular Riemannian foliations, or the Reeb stability theorem for regular foliations, and then there are other stability theorems like the Thurston stability theorems, or developing characteristic classes for the foliations, and so on. There's a huge list of things that you can do once you understand the first step, which is to understand what the Holonomy Groupoid of a singular foliation is, of a singular Riemannian foliation is. And so this is mostly the topic of the talk, to try to understand what this Holonomy Groupoid is. And let me start by saying that we do not have an answer yet. So we do not know what the Holonomy Groupoid of a singular foliation is, but we do know what its linearization or its local model should be. So once you have a singular Riemannian foliation, I'm going to talk about all of this soon, but once you have a singular Riemannian foliation, you can linearize a foliation to get something which is a foliation generated by the flows of linear vector fields in a tubular neighborhood of a leaf or of the closure of a leaf. And for this new foliation, which is also a singular Riemannian foliation, we know what the Holonomy Groupoid is. So this is what I'm going to get to at the end of the talk. So the structure of the talk is the following. I'm going to begin by telling you what a singular Riemannian foliation is. And then I'll tell you about Lie Groupoids and some general results on Lie Groupoids, so as to motivate why we care about getting a Lie Groupoid for a foliation. And at the end, I'll go back to the case of singular Riemannian foliations and explain the work that we did. So I should say some people involved in this project are Marcos Alexandrino, who is the host today, and his former PhD student, because he just finished 2 days ago, Marcelo Inagaki. So many of the results I did together with both of them. And now Mateus Moreira de Mello, who's my postdoc, started working on the project as well. We also have some partial results already. And so these are the people involved. And during the talk, I'll say what was done by which person. Okay. So let me begin with what is a singular Riemannian foliation. So we fix a smooth manifold, and we're going to talk about, I'll tell you first what a foliation is, so a smooth foliation. And I wrote the word geometric here because there are several different definitions for what a singular foliation is on a manifold. And we take a somewhat more geometric perspective. And so let me tell you what this is. I mean, this word is not usually used in the literature. It's just to differentiate from the other notions that you can find in the literature. So let me tell you what this is. This is a partition of M into some things which we call leaves. So it's a partition of M into connected immersed submanifolds. Which is smooth. So it's smooth in the following sense. If you take a vector at a point which is tangent to one of these leaves, one of these submanifolds, then locally it can be extended to a smooth vector field on M, which is always tangent to the foliation, tangent to the leaves of the foliation. Oops, sorry. So this is what a smooth foliation on a manifold is. And we will say that it's Riemannian if, so in this case, the manifold M is a Riemannian manifold. And then a singular foliation is Riemannian if you get a geodesic, which is, so gamma is a geodesic, which is perpendicular at type 0 to a leaf. So this is, sorry, perpendicular to a leaf. Then it's perpendicular in all times to all leaves it meets. So gamma T will be perpendicular to gamma T. So if it's perpendicular to one leaf, it's perpendicular to all of the leaves. That's what a Riemannian foliation is. Are there any questions so far? Let me just say that I prefer having everybody together with me until the point I can reach, then reaching the end of the talk. So if people have questions, please just interrupt me and ask questions.
Yeah, let me reinforce that because Ivan cannot see the chat or anything else on the screen. So if you want to ask him questions, interrupt him, or if you put them in the chat, then I'll have to do it. So you might as well just do it yourself.
Okay. I'll try to keep an eye on the chat. I'm getting good at this doing my lectures online, so I'll try to keep an eye on the chat as well. But if you can tell me, it's good. So let me give you two examples of singular Riemannian foliations. The first one is if you have a Lie group acting on a Riemannian manifold by isometries, then the connected components of the orbits of the Lie group, so the set, so F equals to the set of all, say the connected component of G acting on X is a singular Riemannian foliation on N. So this gives you a bunch of examples, but these are not the most general examples since these are all homogeneous. They're very special examples. And then maybe the first non-homogeneous example is obtained by the following construction. And one of the reasons I'm telling you this construction is because we're going to generalize it later. So you can do parallel transport with respect to connection. The setting here is that you have a manifold, which is a Riemannian manifold. On it, you have a vector bundle with a fiber-wise metric. So it's an Euclidean vector bundle, a vector bundle with a metric on each fiber. And you have a connection, nabla, on this vector bundle, which is compatible with the metric, so metric connection. Then out of this data, you can do two things. First, you can get a foliation on E whose leads, so F is a foliation on E, whose leads, let me call them LE. LE is the set of all points you can obtain out of V doing parallel transport by some path. So alpha is a path in M, alpha of 0 is pi of E. This is pi, the projection map. And so this is a smooth foliation, and it is a singular Riemannian foliation for the Sasaki metric on E. So this is a metric on the manifold E, which is constructed out of the metric on the fiber, the metric on M, and the connection. So using the connection, you get a horizontal distribution, and you can write TE as being the horizontal distribution with respect to nabla, and direct sum with pi star of E. And this comes with the metric because this is just pi star of Tm. So this has a natural metric coming from the metric on M. This has a metric, which is the fiber-wise metric on E. And you declare these two to be orthogonal. Okay, so this is an orthogonal decomposition. This gives you a metric on E. And for this metric, the foliation given by parallel transports along paths for the connection that you have is a singular Riemannian foliation. Okay, so this is...
Sorry, I have a question.
Yeah, sure.
Is it singular? Seems regular.
It's in general singular. I mean, just think about the orbits of the holonomy group on the fiber, right? So the zero of the fiber is a fixed point, and in general, the holonomy group will give you things which are going around the zero, right? And so even on the fiber, it's singular, and then when you extend it, you get things which will be singular, right? The dimension will depend on the dimension of the fiber. Is that clear? So in general, the zero section of this bundle will be an orbit, right? Because it's just a parallel translate of the zero vector. It just stays inside there. And the other orbits will have higher dimension in general.
Yes, it's clear now. Thanks.
Good. Okay, so now I'm going to the second part of the talk. I think I'm doing okay. It's been 10 minutes, right, since I started. And please let me know when my time is almost finished, right? I have a tendency of not keeping too much track of time. So let me go to the second part of the talk, and I want to tell you guys what a Lie groupoid is. So I'll start with a motto, and then I'll give you an example, and then I'll give you the actual definition. So the motto is the following. A Lie groupoid is like a Lie group. Maybe I should put the word Lie here, Lie group. But the multiplication is only partially defined. So this is the motto, and maybe the example to have in mind is the fundamental groupoid of a manifold. And so this guy is composed of all homotopy classes of paths in M, of smooth paths in M, smooth homotopies of smooth paths in M. And if you have two of these paths, say an alpha and a beta, you can compose them as long as the endpoint of one path is the starting point of the next path. And then you get a new path, which is concatenation, which is alpha star beta, which does alpha in twice the speed and then beta in twice the speed. So this is an example to have in mind. You can only concatenate two paths if the finishing point, if the target of one of the paths is the starting point or the source of the other path. And then, of course, you have the path which goes in the opposite direction. So you have some kind of an inverse in this structure. And you have also constant paths at each point. So at each point, you have elements which act like identities. And this is a good example to have in mind when I give you the abstract definition in what follows. So here's the definition of a Lie groupoid, and I'll try to write it while I go. So a Lie groupoid is composed of two manifolds, a manifold G, which we think of as a manifold of arrows. So the points in G are arrows between points in M, which we call the manifold of objects. So each point in G is an arrow between two points say y and z, which are in X. This point is called the source of G, and this point is called the target of G. So these are the two maps which appear here, the source and target map. And these maps have to be surjective submersions. So these are surjective. All the maps are smooth here, okay? Surjective submersions. And then if you have two arrows which are compatible, right? So you have an arrow H such that the target of H is equal to the source of G. Here's the source of H. Then you get a new arrow, which is the multiplication of G and H, which is an arrow from the source of H to the target of G. So this is this map that I wrote here, the multiplication. It's a map from the space of composable arrows to G, and it's a smooth map as well. And then this has to be associative. So if you have another arrow, a third arrow, K, which you can compose, then G, H, K must be equal to G, H, K. And it should satisfy all the properties of a group. So for each arrow, for each point on the base, you should have an identity arrow. So 1Z, the identity at the point Y, the identity at the point X, let's call this X. So each point on N has an identity. This is what I drew in this map here. So each point has an identity, and each arrow has an inverse arrow, which goes in the opposite direction. Let's write it G minus 1. And then the usual things that you expect should happen, right? So if you, for example, multiply G and then do G minus 1, this should be the identity at the point source of G. If you do G minus 1 and then you do G, this should be the identity at the point target of G. If you do the identity times H, this should be just H, and so on. Okay, so are there questions about this definition? I guess not. So this is what a Lie groupoid is. And to every Lie groupoid, you can associate two objects, two structures. One is the orbits of the Lie groupoid. So an orbit of the Lie groupoid is just the target of the source minus one of the point. So let me write this out better. This is the set of all y in M such that there exists an arrow G which starts at X and finishes at Y. So all the points you can attain from X by using arrows of the groupoid, and these are always immersed submanifolds of M. And in fact, if you take the connected components of them, this is a smooth foliation, smooth, singular. In general, it's singular. Could be irregular, but in general, it's singular foliation on M. So this is somehow where groupoids and foliations connect, right? So you have this foliation given by the orbits of a groupoid. And the other structure that you have associated to a groupoid is the isotropy groups. So if you look at a point X, you can look at all arrows which start and end at the same point X. And these form a Lie group with the product given by the product in the groupoid, right? So all of these arrows are composable because they all finish where the other one starts. They all finish and start at the same point. So you can compose them, you can multiply them, and this gives you a structure of a Lie group, which is attached to the point. And these are the two basic structures attached to a Lie groupoid. So let me give you examples, and maybe I think things will always become clearer when we see examples. And so the first one is the following. If you start with a Lie group acting on a manifold M, then you can form a Lie groupoid, which is called the action groupoid, G, of this Lie group action. It's a groupoid over M. This space is just the product of G with M. And the way you think of it is that a pair G, comma, Y is just an arrow starting at Y. So the source is Y and the target is G times Y, is using the action. And then if you have another arrow, here's an X, H, comma, X, such that Y is H times X, then you can multiply them and the product is just GH, comma. So this is, I guess you can guess the inverse and the identities out of this. So this is a Lie groupoid whose orbits or the G orbits for the action, and the isotropy is just the isotropy of the Lie group action, the usual isotropy of the Lie group action. I guess the names orbit and isotropy come from this example. Okay. The second example is the general that I want to give you. Is there are tons of examples, right? So I'm just going to give you a few examples. But the second example is the general linear groupoid associated to a vector bundle. So here E over N is a vector bundle. And then an arrow from X to Y is just a linear isomorphism from the fiber over X to the fiber over Y. So this is what an arrow is. It's a linear isomorphism between the fibers of the vector bundle. And then multiplication is just concatenation of these isomorphisms. The inverse is just the inverse of the isomorphism. The identity at the point X is just the identity map from the fiber to itself. And this is what we call a transitive groupoid. It has only one orbit, transitive, right? And all of the points in M are in the same orbit. And the isotropy, so if you look at G, L, or V isotropy at X, this is just the general linear group of the fiber EX. So this is a groupoid which is somehow appears very naturally when you're studying vector bundles and automorphisms of vector bundles and things like that. Okay, the last example I want to give you is the Holonymy Groupoid of irregular foliation. And for this one, I wrote it beforehand because of the pictures. So let F be a regular foliation, so it's a smooth foliation with all leaves of the same dimension. This is the same thing as an involutive distribution on Tm, an involutive subbundle of Tm. And I drew here a picture of a foliation. And if you look locally in the neighborhood of a point, the regular foliation just looks like the foliation of Rn by k planes, right? It's flat. And then, since locally it's flat, if you have a path alpha, which is inside one leaf, you can break this path into small pieces which are inside these neighborhoods which look very nice, which look very flat. And you can, if you choose a transversal here and a transversal here, you can slide along the path alpha. So you can, if you want, parallel translate alpha to the other plaques of this foliation, to the other leaves, inside each one of these. And you get a map which goes from one transversal to the other, and you can compose them at the end to get a map from T0, the transversal at time 0, to T1, the transversal at time 1. So this map, which I called phi alpha, obviously depends on several of the choices that you made, the choice of the trivialization, the choice of the transversal submanifolds, and etc. But its germ at the point X, which is the starting point of alpha, does not depend on any of the choices that you made. And so this germ is called the Holonymy transformation associated to alpha. And we'll say that two paths have the same holonomy if they have the same holonomy, if the germs of the Holonymy transformations are the same. And then out of this, you can construct the groupoid, which is called the Holonomy Groupoid of the foliation, whose arrows are just the holonomy classes of paths inside the leaves. It's like the fundamental groupoid that I wrote in the beginning, where you took homotopy classes, but now I'm taking holonomy classes of these paths. So let me give you an example of a foliation. So this is the Mobius band. So this is the Mobius band. Oh, by the way, the isotropy of this groupoid at a point X is called the holonomy group. Holonomy group of the leaf L, which goes through X. That's what it's called. Okay, so here's an example of a foliation. This is the Mobius band, and it's foliated by S1s. So here you have one S1. Here you have another S1, which closes when you reach here, and so on. I drew several S1s. And if you pick these as transversals, and alpha is the curve which only goes around once, so this curve, then if you look what happens, so this is like a holonomy is like a first return map for people from dynamics, right? So this is exactly what you're doing. You're perturbating alpha and seeing what happens to this transversal. So once you go around once along this leaf, you're going to hit this point. And if you go around once along this leaf, you're going to hit this point, and so on. But if you go around twice, so if alpha is the path which goes around twice, then you're going to come back at the identity map, right? So the holonomy group of this leaf is just Z2. It's the holonomy transformations are just reflection around the point X. Is this example clear? Does it illuminate things for you guys?
I don't want to ask you to explain again, but so what would be I understand sort of what happens along the red path, but what about, say, the purple path?
Yeah, if you take the purple path, and then you take, let's say, I mean, if you take a loop which is not closed, then this is just the identity map, right? I mean, it has no holonomy. But if you take the path which goes around and closes again, you see that the neighboring paths will do exactly the same thing, right? So the holonomy transformations for the other paths will be always the identity map. So this one has non-trivial holonomy only along this leaf, and all the other holonomies are trivial.
Then I'm not entirely clear what non-trivial holonomy means, right? Because you want to say, let's look at the nearby paths and what happens to them.
Yeah, so let me maybe tell you what the motto is. The holonomy group is telling you how, or the isotropy of the holonomy groupoid, right, is telling you how the nearby leaves wrap around the leaf you started with.
Ah.
Right, so for this one, the nearby leaves, they go around twice, right? I mean, they wrap around by going around twice. Yes. But for the other ones, they wrap around neatly as if it were just a product space.
Yes, that's excellent. Okay, I understand. Thank you.
Good, so that's the motto which is here. So the holonomy groupoid controls the behavior of nearby leaves, and it also tells you the behavior kind of the quotient, right? I mean, this, if you look at the space M mod F for this foliation, it is not a manifold. It's not Hausdorff, it's not a manifold. And the reason it's not a manifold is precisely because the holonomy is not trivial. So that's what's going on. It's telling you that there are identifications being made on the quotient somehow, that things are not gluing well together.
So when you say behavior, you really mean a sort of, what kind of behavior, right? You mean a sort of wrapping behavior.
Wrapping behavior, it's like a dynamical behavior.
All right, so that's why it messes up when you want a quotient.
Yes.
Okay, this is great. Thanks. I think I finally understood this.
Good, great. So maybe we can stop here now. No, I'm kidding. Okay, so here's some nice features that you can do for any Lie groupoid, right? So I mean, there's a lot of differential geometry and theory that has been done already for Lie groupoids, and which you can apply to all of the examples afterwards, right? So here are some nice features. The first thing is that you have a kind of a Lie theory for Lie groupoids. So there is an infinitesimal object, which is just like for a Lie group, you have a Lie algebra. For a Lie groupoid, you have something which is called a Lie algebroid. By the way, a Lie group is an example of a Lie groupoid where the base M has only one point. Right? So this is one of the examples. So the infinitesimal object associated to a Lie groupoid is a Lie algebroid. So this is kind of some sense linear in a sense. So it's an object on a vector bundle, not a vector space, because now you have many identities, right? So just think about Lie algebras. For Lie algebras, you take the tangent space at the identity of the Lie group. And for Lie algebroids, you have to take the tangent space at each one of the identities of something, which is the source fiber, doesn't really matter. But you get something which is linear in the sense that it's a vector bundle. And there are functors which go from groupoids to algebroids. This is a kind of a differentiation functor. And in good cases, you can integrate back to groupoids. So one thing that is very common in the theory of Lie groupoids is you start with a problem involving Lie groupoids, which is non-linear in nature. You differentiate it to get something on Lie algebroids. You solve the problem on the Lie algebroid, and then you try to integrate back to get some. So you try to exponentiate back to get something on the groupoid, to get your answer on the groupoid. And this works pretty well in concrete examples. So this is something that is very well established for Lie groupoids, and it's a very nice feature of the theory. The next thing is that Lie groupoids have invariants. So there are cohomology theories associated, called differentiable cohomology, associated to a Lie groupoid, which can take values maybe in a representation, doesn't really matter what this is. You have a classifying space for a Lie groupoid. Using the classifying space, you can talk about characteristic classes, and so on. I mean, there are invariants that you can easily attach to Lie groupoids. And so for example, if you knew a Lie groupoid associated to a singular Riemannian foliation, this would give you invariants of your singular Riemannian foliation. Okay. The next thing is that Lie groupoids are used to study the quotient space by the foliation, right? So by the orbit foliation. And the idea here is just that, I mean, maybe I'm just going to write something schematic. This is not so important for this talk, but there is a thing called the differentiable stack structure. So this is like a smooth structure on the quotient space. And the idea is that G is an atlas for this quotient space where you remember all the information that you want. So it's like a desingularization. I mean, sometimes you want to work on the quotient space. It's not smooth, but you can work on the Lie groupoid if you do things up to an equivalence called Morita equivalence of Lie groupoids, which just remembers about the transverse direction. So just remembers about the directions in the quotient space. And the fourth thing here is that there is a deformation theory for Lie groupoids, right? So there is a cohomology which controls deformations of Lie groupoids. There's also cohomology which controls deformations of morphisms of Lie groupoids. And you can talk about deformation theory of Lie groupoids. There are quite a few things done in this direction. So here's a place where I worked quite a lot with Mário Skrajnik, João Mestre, which is now in Brazil, João Mestre also, he's a postdoc at IME, and myself, and also with my former PhD student, Christian Cárdenas. And then the last point, which is important for this talk, is the local model for a Lie groupoid. So every Lie groupoid has a local model, and you can ask for theorems which are in the spirit of a tubular neighborhood theorem in the setting of Lie groupoids. So these local models are like first order approximations in the transverse direction of the Lie groupoid, so transverse to the leaves, right? And I'll try to explain what the local model for a Lie groupoid is. Are there questions before I do this? I guess not. Okay. So this feels like my classrooms where I ask if there are questions and I receive I hear silence. So but okay, let's go on. So a Lie groupoid.
I don't have a question, Ivan. Thank you.
Great, thanks, Enrique. Good. It's very hard to give talks not seeing people's faces, right? Maybe most of you guys have gone through this, I guess. But anyways, let's go on. So start with a Lie groupoid G over M. L is an orbit of your Lie groupoid, and then there's a local model around L. Thank you for turning your camera on, Marcus. That's very helpful. And it's something which is linear around L in the transverse direction to L. So how do you set this up? You consider a vector bundle, which is just the normal bundle. Let me write it like this. Normal bundle to the leaf inside of M, right? So this is a vector bundle over the leaf. This is just, if you want, this is just Tm restricted to the leaf modulo TL. It's a vector bundle, let's call this pi. And there's an action of the restriction of the groupoid to L. So this is a transitive groupoid. It acts on E. And what this means is just that for each arrow from X to Y, G, inside GL, you get a linear isomorphism from EX to EY. Linear isomorphism, let's say phi G. So this is what an action is, and then it should satisfy the usual axioms of an action, right? If you act with G and then you act with H, this is the same thing as acting with the product of G and H. And if you act with the identity, it doesn't do anything. Okay. And then the local model, which is like this linear picture that you have. So it's linear in one direction at least. And it's usually denoted by N of GL. This is just the action groupoid of GL on E over L, right? So this is precisely the same thing as I told you about the actions of groups, right? So this is just a set of all pairs G, E, but now you need to be able to act with G on E. So the source of G must be equal to the pi of E. And then if you have an arrow which is G, E, it starts at E and finishes at G times E. Another arrow which starts at E prime, say, H, E prime. Then you get an arrow which is just GH, E prime. It has the same structure as an action groupoid. So this is somehow much more simple than a general groupoid because it's just using a linear action on a vector bundle from a transitive groupoid. So the leaves are very simple to understand, the orbits are very simple to understand, the isotropies are very simple to understand, and so on. This is the gain that you have. Okay. And then, so let me just maybe give you some examples. I think
Ivan,
this will... Sure.
Ivan, can I make a question? Is there some examples of
Lie groupoid without a linearization?
So there are examples of Lie groupoids which are not linearizable. So
Yes.
Yes, many.
No,
So,
I mean without any sub-Lie groupoid that's linear.
Yes.
Wow. Okay.
So I mean, I'm going to tell you what a linearizable groupoid is in a second. A linearizable groupoid is a groupoid which is locally isomorphic to its local model, to its linear model. And there are groupoids which are not locally isomorphic to their linear model and which don't have except for trivial subgroupoids, I would guess, that are locally isomorphic to its model. I mean, you can think about group actions, right? I mean, and this is what I'm going to tell you what the model is now, right? So, I mean, the linearization of a group action is looking at the model on the norm of the action on the normal bundle of a leaf, which is just the Lie theorem. And
Yes.
there are group actions which do not satisfy the Lie theorem.
Okay, yes, that's true, yes.
I mean, you need the action to be
for
proper.
proper groupoids, there should
Proper
always...
groupoids are linearizable. That's a theory.
Okay. That makes sense. Thank you.
Okay. So in
Ivan,
the case...
I have mixed feelings because I really want to see the examples, but we have 10 minutes to work on. So can you manage that somehow?
Yeah, I guess. I think the examples are maybe important to understand the rest, and then I'll just run through the rest maybe a bit. We have 10 minutes, yeah, it's been 40 minutes already. Okay. So let me tell you this very quickly, okay? So just what's going on. So if you look at the normal bundle to a leaf here, this is just the associated bundle with respect to the action on the normal space, right? So this is an associated bundle. So you have a principal bundle G over the orbit with structure group Gx, and this comes with a normal, then action on the normal space, the isotropy action on the normal space, and then there's an obvious action of G on this space, which just acts on this component, and the local model is just the action groupoid for this very simple linear action so it's the action which comes from the slice action. And for the holonomy group of a foliation, there's something similar, and I'm not going to explain because of time, but the normal space comes with a very simple linear foliation, and this linear foliation, the holonomy groupoid of this linear foliation is just the foliation, the local model for the holonomy groupoid of the foliation we started with. So this is what Marcus had asked, right? So a Lie groupoid is linearizable around the leaf if it's locally isomorphic to the local model. And there's a theorem which states, so there's a theorem which is actually, it started with Alan Weinstein, and then Zung proved the technical part, the hard technical part. The proof was quite a lot of analysis, and it was a hard proof, and then Marius and I gave a geometric proof using the deformation theory for Lie groupoids. And then Matias Del Hoyo and Rui Loja Fernandes gave an even more geometric proof using Riemannian metrics on groupoids. Their proof is very nice. If you're going to read some proof, read their proof, which is the nicest proof. But the theorem states that if you have a proper groupoid, so a groupoid for which this map source S, T is proper, then it's linearizable, and this reduces to the Lie theorem and the reducibility theorem for group actions and foliations. Okay. And along the same spirit, there's a theorem I wrote here, which is a theorem I have together with Mateus, which is a theorem about Lie groupoids with an extra structure, with an extra Riemannian metric, which is compatible with the multiplication of the groupoid. And it has to do with the leaf closures of the foliation it induces, but I think I'm going to have to let you guys just read it while I explain the next part. But it essentially tells you that the leaf closures of the local model are itself a smooth foliation with a Lie groupoid given by the closure. You can form a closure of the groupoid giving you the groupoid, which gives you the leaf closures. So in a sense, it gives you, well, it gives you the structure of the leaf closures of the orbits, which is something people in Riemannian foliations are very interested, actually. Okay. So finally, I'm at the last part. I have 6 minutes. I think it's fine. So I want to tell you what the linear holonomy of a singular Riemannian foliation is. And so we call that a singular Riemannian foliation is a foliation on a Riemannian manifold with some extra properties. So geodesics, which are perpendicular to a leaf, they stay perpendicular to all leaves. And for these singular Riemannian foliations, there is a very nice semi-local description. So a description around the leaf, or around the closure of the leaf, actually, which is given by Marcos Alexandrino and Marco Radeschi in their paper, and also very well explained, and some more things were proven by Marcelo Inagaki in his thesis he defended on Wednesday now. So it's, I mean, if you're going to look somewhere, look at the thesis, and he has some very nice drawings also of singular Riemannian foliations. The thesis is very well written. Okay, so you fix a leaf of your foliation, and we want to describe the foliation itself on a neighborhood of a closure of the leaf. So on the closure of the leaf, on the space B, which is the closure of a leaf, you have a regular foliation by dense leaves, just restricting your foliation. And you can consider its normal bundle, which is just the orthogonal bundle in this case, which is a vector bundle. It has a natural metric because it's the orthogonal bundle to B, right? And you can identify this normal bundle with a tubular neighborhood via the tubular neighborhood embedding. And so the foliation you started with on F will give you a foliation on this vector bundle. And this foliation is the one which has a nice geometric description as follows. So E comes, this vector bundle comes with a partial, an FB partial connection. So this is just a connection where you only differentiate along vectors which are tangent to the foliation FB. So this is a vector bundle over B. Section is a V. The section is a V. And also this foliation you have on E induces foliations on each fiber, EB, for each fiber. And so you can describe the foliation FE just by knowing the two data above. So the leaves are just the parallel translates of leaves of the leaves. So LE leaf of FE restricted to EB, just the leaf inside the fiber of the vector bundle, and alpha is a path starting at pi of E. So it's like the first example we gave, but this is a path inside the leaf. It should be inside the leaf. So you can only parallel translate along paths which are inside the leaf. Okay. So this is the geometric description, and this foliation Fe can be linearized. So there's a process of linearization using homotheties to get a linear foliation on this vector bundle. And by linear, I mean a foliation which is generated by flows of linear vector fields. So vector fields whose flows are so infinitesimal automorphisms of the vector bundle E. And this foliation has a very nice geometric description as well. So I'll just give you the geometric description, which is the following. So K, if you consider the following group, K0 of B is the maximal subgroup of isometries fixing leaves of this foliation Fe restricted to EB. And then the foliation, the linearized foliation, is just the parallel translates of the orbits of this group. So this is the foliation. And it's somehow a very simple foliation, but it captures a lot of the geometry of the original foliation. I think I reached my time, or I'll reach it in, yeah, I reached my time. Can I have 3 more minutes to finish the talk?
Marcus, you're the chair.
If I am the chair, yes, of course.
Okay, so I need just 3 more minutes
Yes,
to tell you what the holonomy groupoid is of this foliation. So the point is that all of these groups, K0b, are isomorphic. It doesn't depend on the point you have. So for all B and B prime in B. And somehow using this, so if you look at the Lie algebra of these groups, they contain the Lie algebra, the holonomy algebra of the connection nabla of this foliation. And you can use this to create a distribution, which is, so you take horizontal lift with respect to this connection, and you take direct sum with this vertical part, which is just the Lie algebra of these groups. And this is an involutive distribution on the orthogonal frame bundle of V. So this is the ON frame bundle. So what's going on is that you get actually, you can lift your linear foliation to a foliation on the orthogonal frame bundle, which is regular. And now for this foliation, you have a holonomy groupoid because it's a regular foliation. So you can take the holonomy groupoid of F tilde. The group, this is a groupoid over the orthogonal frame bundle of V. And ON acts on this groupoid by isomorphisms, by automorphisms of the groupoid structure. So you can take the quotient. This is just B. And now this groupoid acts on E, and you can take the holonomy groupoid of the linearization to be the holonomy groupoid of F tilde modulo ON acting on E. So it's like a local model groupoid, right? It's an action groupoid by linear action. And the theorem is that this is a Lie groupoid whose orbit foliation is the linearized foliation. And something I proved after we wrote this with Mateus is that this is actually the smallest possible such groupoid. So it really is like the holonomy groupoid of a regular foliation. And I guess this is it. Sorry for being over time, and thank you.
So thank you very much. There are more questions, remarks?
I think we have to applaud first.
So there are more questions, remarks?
I have a question.
Yes, please.
It's a question that only reveals my deep ignorance. What's the perspective of having a Berger listoid? You know, are we anywhere near understanding which having a systematic classification of which structures can be holonomy groupoid.
I mean, so I guess there are two things involved here. Okay, so one is holonomy of the connection, the other one is holonomy of the foliation, right? So
Right.
I mean, for foliations, you can have. I mean, it's quite wild. I think you can have. I mean, I don't know. I would never guess how to answer that. I think maybe the question you might want to ask is, given a foliation, right? So you fix the foliation and you want to look at the holonomy in the sense of connections, the possible holonomy groups of foliated connections on this guy. And so then you want to do something like Ambrose.
That's what I meant. That's what I meant.
And then you want to do something like Ambrose. So what I can tell you is that this construction of this groupoid, so essentially the part where you consider this can be interpreted as a generalization of the Ambrose-Singer reduction theorem for foliated connections. So this is one possible interpretation. Is actually one of the ways we thought about it to reach the theorem, right? So this is.
So do you then have a class of theorems that say the curvature of said connection must lie in some subspace?
Yeah. So the point is the following. I mean, for each leaf, you will have a holonomy Lie algebra, right? Which is a connection restricted to that leaf. And in general, these might not form a Lie algebra bundle, right? I mean, they might not be the same Lie algebra. It's easy to construct examples where this varies from one leaf to the other. So if you want to do
sheaf of Lie algebras.
Yeah, it's like a sheaf of Lie algebra, I guess. Yeah. But one thing you want to do if you want to get reductions or things like that, you need to have them all inside something which is really a bundle of Lie algebra, so you can reduce the structure group, right?
Yes.
And this is the role of this Lie algebra K in this setting. For singular Riemannian foliations, you can do that. There's a natural bundle of Lie algebras in which each one of these holonomy Lie algebras fits into, and then you can do this reduction kind of as if you were doing it leaf by leaf.
Well, then it looks kind of good, right? Because if you have a sort of Ambrose-Singer setup available, then you could actually try and set out and classify.
Yeah, I guess you could do. I mean, you could try to find obstructions for having these reductions and
yes.
and do obstructions.
As far as I know, the only results talking about restriction of the curvature if the ambient space has bounded curvature. So this curvature inside of the foliation is also bounded. So the curvature of the ambient space implies that this curvature induced by this connection tau, the connection inside of the foliation is then bounded as well. So
yeah, but bounded is a kind of metric phenomenon, right? I was looking at something more representation theoretic, right? I want to say that the curvature lies in a certain subspace, right? That's when Ivan mentioned Ambrose-Singer. Yeah, I think that's the right mindset, right? You want to say that the curvature can't just be anything, and you know, it's a reduction. It's a reduction.
Yes, of course. Yes.
Yeah. Are you guys looking into this? Is this actual research, or am I asking sci-fi here? I don't know how hard it is to progress in this direction.
We haven't looked into this. We have not looked into this so far. But I think it's a very good question. I think it's something that should be looked into.
Okay. Maybe a student should do this.
Maybe. It was already... Leonardo and Icaro and I have worked a little with this approach to bound this curvature of tau to control things like mean curvature flow. So in order to control that in non-compact space, we have this other approach using bounded geometry. But until now, we didn't have studied. We don't have studied curvature in the sense we didn't try to classify anything.
But let me tell you something, Henrique. I mean, the language of Lie algebroids and groupoids is very much fit to try to answer the question, right? So there is a Lie algebroid called the Atia algebroid of your frame bundle, right? Which is the natural recipient of connections. So connections give you maps into this Lie algebroid. And if you have a foliation, you can look at maps, you can restrict this algebroid to the foliation and you get another Lie algebroid, which is the recipient for foliated connections. And now, once you have these maps, you can look at their images and this will give you a sub-algebroid, which you can use to try to reduce the structure group of the principal bundle that you started with. So that's kind of that's kind of what's going on in the proof of this anyways. So this is the natural recipient for studying the problem you're proposing.
Cool. Good stuff. Let me think about this for a year. But I think you may be onto something here in that other direction. It's the Berger listoid, as I call it.
Yeah, I just put oid after everything, and it sounds.
If you have a fiber bundle and a connection compatible with a metric, do you have some kind of classifications for possible holonomies there?
Yes.
So this should also have.
Yeah, that's Berger's list.
Because if the leaves are dense, then the partial connection is in fact, or should be, that is what I sent Ivan yesterday, a restriction of a metric connection with respect to the base. So it may work in that direction.
Let me think about this. Yeah, let me think about this for half a year. But
okay, but the question, I can reduce the question as the following. Say what you can say about a fiber bundle where the connect with a metric connection. That is the question.
Yeah, but Marcus, I think the interesting case is not the case of dense foliations, right? I mean, which is the case that you sent me yesterday, right?
One of the cases, at least it goes in the directions of Henrique. And these foliations that are dense are called the minimal for some reasons. So the people with the foliations started to study them and then make the things complicated. But that's probably the first question.
Yeah, no, I think it's the simpler case. I agree.
Yes, and it's a natural case. If you can say in a few months what you could say about metric connections, and classifications of metrical connections, there should be similar results in the case where you have foliated connections with where the base is where you have a minimal foliation in the bases, in the sense that the leaves of are dense. This is essentially that should work.
I mean, just to stress what Marcus is saying, what he's saying is that in the case of a dense foliation, so in the case that we're dealing with in this talk, the connection is actually the restriction of a global connection, right? This is not usually the case, but there is a global connection on the base B, which when restricted to each of the leaves gives you this connection number. So this is something that we didn't know at the time when we wrote the paper about this, but that Marcus sent me a LaTeX version of this yesterday. So for those, you can try to understand what the relation between the holonomy of this global connection is and what the holonomy of each of the restricted connections is. And
Can you compute the curvature? Can you make sense of the curvature as a true tensor in some sense? It's something that maps two planes.
It should be possible. Yes, it should be possible.
Yes.
It should be possible.
Yeah, if one looked at that, then the representation theory should decompose this object into irreducible components, and that would be the first step. So if you can write down the curvature and sort of split it blockwise using some representation theory, and you could identify what these blocks are, that, I mean, that would be where to start. It's the second order information here. You can get away, you know, unless you want to do something like Green's theorem and pass from paths to the region between them. You can, holonomy is like a first order phenomenon, but if you can compute the curvature, then it's the representation theoretical decomposition of this second order object that dictates if you can follow a program like Berger or a subclassification program or not.
Right, guys.
Yeah, let me think about this. I mean, maybe it's bollocks, but there's a chance you could do a lot of research here.
Nice.
Okay, thank you. Some more questions
from, yeah.
Oh, sorry.
Yes, I have a question.
Sure.
You said that if you have a Lie groupoid, which is proper,
yeah,
then you can linearize it.
Yes, around
so
the
you have, around G-split. So you have local ES slice, right?
Yes.
Is it an if and only if? Because in the case for group actions on compact or for
no,
group actions,
it's not if and only if. So, for example, the theorem that actually Matias Deloyo and Rui Loja Fernandes proved is that if you have a compatible Riemannian metric, so these are very nice metrics for which the normal exponential map or Lie groupoid morphisms, right? So you can like exponentiate keeping the structure of the Lie groupoid, and the theorem they proved that these are already linearizable, and then every proper groupoid is an example admits such a metric, but there are groupoids which admit such a metric which are not proper, and they are linearizable. I mean, you can let me just give you actually a much simpler answer, right? So if you have a proper groupoid, then the isotropy groups are all compact. Now just start with a non-compact group acting by a representation of a non-compact group and take the action groupoid. That's already linearized because it's already a representation of a group action from a group which is not proper because it's from a group which is not compact. So the isotropy at the point will not work. I mean, this will not be a proper groupoid.
Okay. And is there a hope kind of to distinguish which are proper and which are not, which Lie groupoids? Yeah,
so this theorem I told you that I did with Mateus, so maybe I'll just put it here again. So this we're actually trying to understand precisely your question, right? So well, almost precisely your question. So we're trying to understand how far a Riemannian groupoid is from being proper. And these are most of the examples of linearizable groupoids, right? So I don't know, maybe Mateus can tell me if there are linearizable groupoids which are not Riemannian. I don't know if that's true or not. But he's here listening. Maybe he wants to say something. But I mean, we're trying to understand how far a Riemannian groupoid is from being proper. These are maybe the largest class of linearizable groupoids. And so what we're getting is that, I mean, the Riemannian groupoid might not be proper, but it still sits inside a general linear groupoid. And if you take its closure, this becomes a proper groupoid. So, I mean, it's not exactly proper. It could have some non-effective part, which is the kernel of this map psi. So a part which is, you don't see it because it's not actually acting, right? It's non-effective. And this part can actually be very big, right? I mean, there's no problem in putting something huge there. But the effective part, you can take the closure to get something proper. And this is kind of measuring how far the groupoid was from being proper to begin with.
Okay.
I don't know if I answered your question.
Partially, yes.
Okay.
So do we have more questions, remarks? So let's thank Ivan again.
All right.
Thank you. Thank you.
All right. Thank you, Ivan. Thank you, everyone. And let's meet again